Hello, my friends, and welcome back. Mr. A here with another new name tag. What do you notice about this one? Besides my name on it, it has a bunch of zeros and ones on it. I wonder why that could be. Well, that's because today we're going to be discussing numbers in a special way that computers count and think, called binary numbers. Before we get to binary numbers, think about the numbers that you already know.
There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on.
Well, these numbers that we all learn when we are young have a name also. They are called decimal numbers. The deci portion of decimal comes from the Latin term decimus. Kind of makes me think of a superhero. It's a cool superhero name, don't you think? I am Sir Decimus. Fear me. I am Decimus. I can count to 10. Decimus actually means tenth or 10. Let's think about how we count in the decimal system while we're writing the numbers down.
If we start with 0, then we got a 1, then we got a 2, then we got a 3, 4, 5, 6, 7, 8, 9. But then what happens next? We don't know what the next number is. It's 10, right?
Which is represented by a 1 and a 0. Let's keep going and let's see if we recognize a pattern.
11, 12, 13, 14, 15, 16, 17, 18, 19, and then what comes next? 20.
I'm going to point out a few things here. Let's look at this. We look at these numbers here, and we go all the way up to 9, and then we have a 1 here, and we start over with those numbers again on that back side, don't we? And we go all the way up to 9 again, and then this number changes to 2. And we start back over, because if you remember, what comes next is 21, and the pattern just keeps repeating over and over again. Did you know that we have a term for these spots? They're called placeholders. I'm going to move over to here, and we're going to look at our decimal system that we're all so familiar with. It's also called base 10. I think you can probably figure out why it's called base 10. And if we think about the placeholders, so if we write a number, right now we've wrote a bunch of numbers in decimal, but let's write a number, let's say 365 days in a year, and we think about that number down here. Well, that's 365, okay? And we look at it, 5 is in what we call the ones place, which means that we just take this number and multiply it by 1. 6 is in the tens place, which means that we multiply 6 times 10, and 3 in the hundreds place. Now, I know some of y'all may not know multiplication yet, and that's not a big deal, because I'm gonna give you just a real quick lesson. But if we think about this from a placeholder standpoint, and we have 5, we have 1 5, so one group of 5, so we're gonna have 5 there. And then we have 10 sixes, or 6 tens. Can you count by tens yet? 10, 20, 30, 40, 50, 60. So this represents 6 tens, or 60. And then this is 3 100s. Now you may not be able to count by 100s yet, but it's pretty simple. 100, 200, 300. So this 3 represents 3 100s, or 300. Now I know y'all know how to add. And guess what? If we take that 5 and we add it to that 0 and 0, we get 5 there. Add that 6 to that 0, we get 6. And then there's nothing to add to that 3, so we get 3. 365. So we represented that number broken out by its placeholder. Placeholders are pretty cool when you think about it. And knowing about placeholders is what allows us to represent systems of counting other than decimal. Remember me saying that decimal was based on 10? Remember deci? Sir Decimus? I need a pencil. Sir Decimus? Well, there's a lot of other counting systems than decimal, and they are all based on other numbers. For example, there is one called octal. Does the first part of the word octal make you think about something else? Octopus? Well, how many tentacles or arms does an octopus have? 8. That's right. Octal is a counting system based on the number 8. Weird. There's also another system called binary. And if you think about the word binary and it starts with bi, is there another word that maybe we ride and we pedal that uses the word bi or starts with the sound bi? Bicycle. We use that term because on a bicycle there are 2 wheels. Binary is based on the number 2. I'll show you some more about binary in a little bit. But first I want to introduce another one of my best friends that I work with every day, Miss Lori Kagebein. Miss Lori teaches high school students and teaches all about computer science. But today she's made a special video to help explain how computers use binary.
Hello, my name is Lori Kagebein, and I am a computer science specialist in Arkansas. I love programming computers and talking with people about computers. Computers do not communicate like we do. They have their own special language. Today, I thought we would learn a little bit about that language, and I know the perfect person to teach us. We're going to visit a very friendly computer, Chip. Let's go. That was fun. Now let's find the computer, Chip. Do you see him? Chip is a laptop. He is gray and black. What? You found him? Yep, that's Chip on the desk. Great job. Hello, Chip. It looks like Chip is asleep. Do you know how we can wake him up? Chip! Nope, that didn't work. Do you have any ideas? Press the power button. That's a great idea. Pressing it now. Hello, Chip.
Hello, Lori. Looks like you brought some friends with you today. How can I help you?
Well, Chip, I was hoping you would tell our friends about the special language computers use.
I would love to.
Take it away, Chip.
First, let me introduce myself. My name is Chip, and I'm a computer. Computer Chip. I love to talk with people about computers. Right now, I'm speaking in English, but that is not my native language. Computers communicate in a language known as machine code. Machine code is based on binary, and binary relies on bits. Bits are known as flip-flops because they flip and flop between two things, on and off. Would you like to meet a bit? Here are 2 bits. Each bit is in a different state. One bit is on, the other is off. Can you tell which is which? Computers read the flip as a 1 and the flop as a 0. So, with one little bit, 0, 1. A computer can count to 1. Wait, that's not very impressive. How can computers get anything done if they can only count from 0 to 1? What's that bit? That's right. Bits like working together. Let's call in some more bits and see what happens. We have 1 bit and it's off, so we have the binary number 0. We flip our 1 bit to on and we have the binary number 1. We call over an off bit to link with our on bit. We flip the new bit as we flop the old bit, which results in the binary number for 2. Now, flip the old bit and we have the number 3 in binary. We have again used all our flop and flip options, so we call over another off bit. Then we flip the new bit and flop the old bits to get 4. We can keep up this flipping and flopping of bits, calling new bits when needed to keep counting higher and higher. To see this, let's see if we could count to 10. I'll count to 10 on my screen using decimal numbers. Decimal numbers are the numbers humans like to use when counting. They are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The bits will count along using binary. They'll need to work in a group of 4 in order to count to 10. 0. Looks like the bits are ready. Are you ready? Looks like everything is ready to go. Great, let's count. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9, 10, 10. That was fun. Great job to you and great job to the bits. Let's see that one more time. Counting to 10 in binary. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I hope you had fun learning how to count to 10 in binary. Come back again and we can look at how we can use binary to represent colors and letters. Goodbye.
Chip has gone back to sleep. We will leave Chip here and head back to my office. I hope you had fun learning computer science. See you next time.
Thank you, Miss Lori, and thanks for introducing us to Chip. Computer Chip is pretty smart. Binary seems pretty cool, and counting in it seems neat, but let's take a closer look at how it compares to our decimal system. If you remember from our decimal system discussion, decimal is based on the number 10, and the placeholders are all based around that. We have the ones place, the tens place, we have the hundreds place, and we didn't discuss this earlier, but we have the thousands, 10,000s, and guess what? It keeps going. When binary, we can only use 2 numbers, 0 and 1. So in all the placeholders, they have to be based on 2. We still have the ones place, but then we go to the 2, and then the 4, and the 8, and so on. Like in decimal, the first spot is the ones place, meaning whatever is in this placeholder is just multiplied by 1, or it's just itself. But this can only be 0 or 1 in binary, because remember, In binary, we only have 0 or 1 that are numbers. The second spot is the 2's place, meaning whatever is in this placeholder is multiplied by 2. But again, remember, it can only be 0 or 1 in binary. It is pretty easy if we put a 0 there to understand that this is 0, then in that place. But if it's a 1, it's a 2. The third spot's where it gets tricky. But if you don't understand that right now, don't worry. So, just like we did for decimal, we're gonna try to look at a binary number and come up with a value that we understand. So I'm gonna write a number out, and remember, this is a binary number. Okay, it's a binary number. So if I wrote out 0, 1, 1, and we just do that. Now, if we were in decimal, what would you call this? You'd call this 110, right? But we're in binary, so it's not 110, which I know doesn't make a lot of sense right now. But let's look at this over here. Let's think about it from our placeholder discussion. Okay? We know that this is the ones place. So if we say we have 0 ones, how much do we have? Well, 0. Okay? We have 0 ones, so we have 0. Now, this is the 2's place, okay? So if we think about in decimal number system that we have one number 2, then what do we have? We have 2, right? And then here we have one number 4, so we have 4. Now you see, if we went on up and we had said 0 and 1 there, then we would have 0 eighths or 0, and then we would have 1 16. Okay, so this would be this 10110. Let me add that up there. This would be that represented in our decimal system, or thinking about it in our decimal system. So let's see what 10110 in binary equals in decimal. And we can do that simply by doing this placeholder conversion and then adding all this up. So we have 0 plus 2, which is 2. We add 2 to 4, which is 6. 6 to 0, which is still 6. And then we have 6 plus 16. So I'm going to pull this 6 down here so we can see it. And I'm going to say 16 plus 6. And if you know, that's going to be 12. We carry the 1, right? So that's what? 22. Okay, so this number, this binary number, 10110, in decimal equals 22. Kind of weird, but if you don't get it right now, once again, don't worry. The main thing for you to take out of this video is that there are different ways to count, and there are different number systems, and that computers take everything down. Everything you do on a computer is taken down to ones and zeros, because that's all it understands when it gets down to the very base level of how it works. It only understands 1 or 0, just like those bits that are on or off in Miss Lori's video. Well, that's all the time we have for today, friends. We'll see you real soon on our next episode of Computers Are Fun.